class, I want to cover 1.3 properties of functions. And this section has a lot in it. It has determine even and odd functions from a graph and from an equation. Use a graph to determine where a function is increasing, decreasing, or constant. Use a graph to locate maximum and minima, an absolute maximum and minima. And then use your calculator to approximate local max and local mins and to determine whether a function is increasing or decreasing. And then the last thing is find the average rate of change. So that's a good bit of stuff. So to obtain the graph of a function y equal f of x, it is often helpful to know certain properties that the function has and the impact of these properties on the way the graph will look. Okay, so even and odd functions. A function f is even if and only if whenever the point xy is on the graph of f, the point minus xy is also on the graph of f. Using function notation, we defined an even function. So an even function is going to look like this. It's going to be symmetric with respect to the y-axis. That is one example of an even function. So if it has like, say y equal x squared is the function, and say it goes through the point 2,4, it's also going to go through the point minus 2,4. And so that's what we mean when we say even. So it's really symmetric with respect to the y-axis. Okay, for the even function shown in figure 17a, notice that f of x1 equals f of minus x1. So here, this is an even function. This one's even. And yes, if we've got x f of x, we've got minus x f of minus x. So basically, the x and its opposite have the same y value. And then a function is odd. So let's talk about odd. The next graph is an odd function. A function f is odd if and only if whenever the point xy is on the graph of f, the point minus x minus y is also on the graph. Using function notation, we define an odd function as follows. A function f is odd if for every number x in its domain, the number minus x is also in the domain and f of minus x, f of minus x equals minus f of x. This is the same thing as we would call symmetric. With respect to the origin. The right way. Okay, so it says for the odd function shown in figure 17b, notice that f of x1 equals minus f of x1, which is equivalent to f of minus x1 equal with the minus sign outside f of x1. So basically what we're saying, that if you have the opposite of x, you have the opposite of y. And if you look up here, this is an odd function. And it has, like say x1, f of x1, it has minus x1, f of minus x1. Now, also, it is symmetric with respect to the origin. If you turned this part over and then turned it over this way, this part would end up on that. So, well, an odd function an example of an odd function would be y equal x cubed. That's an example. And it goes kind of like this. It's symmetric with respect to the origin. So if it has a point on here, say 1, 1, it also has the point -1, -1. So if it has the positive x and y, it also has a negative x and y. And that's what we mean by odd. Okay, so let's determine whether these functions are even or odd. Okay, so is this symmetric with, I mean, because you can look at it, the first thing you can do, you can look at it and just see if it's symmetric. This one is symmetric with respect to the y-axis, so it's even. It's symmetric with respect to the y-axis. And also, if we have xy as a point on the graph, then we also have negative x, positive y is on the graph. Okay, and that's an even function. So what we're saying here is that f of negative x equals just f of x. So, like, let's see if we can find a point on here. What's a good point? It looks like it goes through the point, what is that? 1, 2, 1, 2, 3 over and 3 down, maybe? Or 2 down. I think it's 2 down. 3 over and negative 2. And over here, it would have a 1, 2, 3, a minus 3 over, and a minus 2 down. And whatever this point is, it looks like it's it's 2, and then not quite 2, like maybe 1.8 or something. Over here, if you have minus 2, you have that same y value. Okay, so that's what we mean by even. Oh, here was a point I could have used right here. Let's use that one instead, since I don't really know if that's 2.18. I can't really tell. Let's use this one. So this point is 1, 1. This point right here is minus 1, 1. Okay. Now, let's look at this example. Sorry about that. Let me get back to my thing. Hold on just a second. Okay, so if we look at this example, I can see that it does look like it has the odd symmetry. It's symmetric with respect to the origin. And you can see on here that it has a point 2, negative 3. So if we're right at 2, I think it's 1, 2, 3. This is the point 2, negative 3. Okay, so it should have the point 2, 3. 2 over and 3 up, and it looks like it does. That's the 0.2, negative 2, 3. So you see, if you've got a point, then you've got the opposite of that point as well. And so this is odd. So if you have xy, that means that you have minus x minus y. And it also means, if you think about it this way, that f of x or f of minus x equals minus f of x. So if you take the opposite of the x value, like I did here, you get the opposite of the y value, like we got right here. Okay? Let's see what we've got next. That was where we were looking, and still, I guess we still are looking at functions and figuring out whether they're even or odd. So let's look at this. That shouldn't be right here yet because we haven't talked about increase and decrease. Okay, a function. You know what? Hold on just a minute. Okay, we can also determine even and odd functions from an equation. So here we have the equation of the function, and we want to figure out if it's even or odd. Neither. It could be neither. So the way to do that is to go f of negative x, and then you have to put negative x everywhere there's an x. And you know, when you raise a negative to an even power, it becomes even. And you could raise that to the fourth power. If you write four negative x's next to each other and multiply, it's going to come out even. Same thing here. So this is going to be an x squared. But this is the same thing as what we started with. Well, that's what it means for a function to be even. So this is going to be even. And what happened here was f of negative x equals f of x. You might also notice that this function, so this is what the function was, f of x equals 2x to the fourth minus x squared. That was the function. So I'll just write it again. Notice something about the exponents. Do you notice that the exponents are even? So if you've got the equation of a function, if all of the exponents are even, then it's going to be an even function. So let's look at this next example. This is f of x equals x plus absolute value of x. So what we want to do is we want to substitute in a negative x. So everywhere we have an x, we're going to put in a negative x. Now, when you take the absolute value of a number, it doesn't, you know, like if you had the absolute value of -2 and the absolute value of 2, they're both going to give you positive 2. So really the absolute value of negative x is just the same thing as the absolute value of x. So if you look at this, it's not the opposite of what we had, because every term would have had to change signs. So it's not true that f of negative x equals the opposite of f of x. So it's not odd. And it's also not true that f of negative x equals the same thing as f of x, like in the first example. Neither one of those are true. So what we say is this is neither. It's neither even nor odd. And plenty of functions are neither. So this is neither. Now let's look at this third function down here. And we've got g of x equals the square root of x. So let's put a negative in here. So we'd have g of negative x equals the square root of negative x. That's an equal sign right there. So let's think about this for a minute. Now, it's say we had x equals -4. So then if we did g of minus a -4, because we're doing the g of the opposite, that would be equal to the square root of +4, which is 2. Now also look at what g of 4 is. It would be equal to the square root of 4, which is 2. So it looks like if you take the square root of a number, the y value is going to be the same as taking the square root of the opposite of the number. Now, let's think about that because, so what we didn't put a -4 under the square root. The domain of the function would change if we've got negative x. So it looks like this kind of, and it has the point 2, 4. And then it has on the other side, it has the point -2, 4. And this is y equal the square root of x. And this is y equal the square root of -x. So see that the domain changes if we put in negative numbers. So really but the y value is the same, isn't it? So what we're saying is f of -x is the same as f of x. The y value stays the same. Now, do you think this is even or odd? Well, look at the symmetry of it for one thing. Isn't it symmetric with respect to the y-axis? Sort of. So it is symmetric with respect to the y-axis. This is also true. That means it's even. This function is even. Okay, let's look at the last function. And we've got h of x equals x over x squared minus 1. Okay, so if we go h of minus x, we have a minus x over a minus x squared minus 1. So we would have a minus x. Now when we square, it becomes positive. And this is actually, because this minus sign, you can write out front of the whole thing. So what we've really said here is this is going to be the opposite of f of x. Because you see what you got here is a minus sign in front of that. So when you put the minus sign in, this gets squared, and so it comes out the same. But there's a minus sign in front of the function. And so this is the opposite of this. Now, what does it mean when f of negative x is equal to the opposite of f of x? What does that mean? That means it's odd. Okay. Let's look at the next page. Okay, so here we go. So a function is increasing on an interval I if for any choice of x1 and x2 and I with x1 less than x2, we have f of x1 is less than f of x2. So basically what that's saying is that as the x value gets bigger, the y value gets bigger. Now, a function is decreasing on an interval I if for any choice of x1 and x2 in I with x1 less than x2, we have f of x1 less than f of x2. So that what that means is if the x's are getting bigger, the y's are getting smaller. A function is constant on an interval I if for all choices of x in I, the values of f of x are equal. And that would look like, you know, it would be y equal some number like y equal 3. It would be a constant function. 3, something like that. Okay, so that's one property of a function. The next property, and we're going to talk some more about increasing and decreasing. But the next thing we're going to talk about is here we go. Using a graph to locate local maximum and minimum. Okay, so suppose, let me get it over a little bit. Suppose f is a function defined on an open interval I containing c. If the value of f at c is greater than or equal to the values of f on I, then f has a local maximum at c. So what this means is that if at c, the values to the left and to the right, the y values to the left and to the right are less than the y value at f of c, f of c is greater than these other y values, which it looks like right here. This is what we call a local maximum or max at c. Now, what the local max is, so it's a local max of, let's put that in there too, of f of c at c. Okay, so sometimes because the idea of local max and mins is really important in a lot of applications in business, in manufacturing. You want to find out where, especially where your absolute max and absolute mins are. So one thing that's important is that, you know, like which value is the maximum and which value is where the maximum occurs. So we say the maximum occurs at C, but the maximum is f of C. This is important, like say you're in business and your manager wanted to know what number of cars we need to sell in order to maximize our profit. So C would be the number of cars and f of C would be the profit, and there would be some kind of equation relating them. So this is a local max. Likewise, if the value of f at c is less than or equal to the values of f on I, then f has a local min at c. So if you're right here, and if your y values to the left and to the right are greater than your y value at C, then that is a local min. So it's a local min of f of C at C. Okay. Now, that's what we mean by local max and local min. Now, there's also, well, we don't talk about that yet. Let f be a function defined on some interval I. A function f has a local maximum at C if there is an open interval I containing C, so that for all x in this open interval, we have f of x is less than or equal to f of C. We call f of C a local maximum value of f. This is just a different way to say it. A function f has a local minimum at C if there is an open interval in I containing C, so that for all x in the open interval, we have f of x greater than or equal to f of C. And we call f of C a local minimum value of f. So we're talking about the local mins and the local maxes. And let me tell you this. You can't, and I'm going to talk about absolute max and absolute mins in a minute. But you can't have a local max or a local min at the endpoints, because you see at the endpoint, there's nothing to the left. So you can't say that this point is higher than the values to the left and higher to the values to the right. Plus that point isn't even on the graph because it's got an open circle. So that's one thing to remember, that local max and min will not occur at the endpoints. Okay, let's see what's on the next page. Okay, so we have an example. Now then it says use interval notation, and let me see. Use interval notation to write the intervals over which f of x is increasing, decreasing, and constant. So you always go left to right. You always read a graph left to right. So if we look at this first graph, it starts off increasing. So from here up to right here, it's increasing. Now that interval, and remember in the interval notation, we put the x values. This x value right here is a -5. Is it keep going? You know, it's got the error. So it's I just noticed it actually does have an arrow here, not a point. And this is an arrow here. It's kind of hard to see. So then really it's going from negative infinity up to this x value. So it's increasing from negative infinity to -2. And then it's constant. So where is it increasing again? It's increasing again right here at, I believe it's 2. So you put union with 2, and then this line keeps on going. And so that's to infinity. So right here it's increasing, and right here it's increasing. Now, what's it doing from here to here? It's constant, isn't it? So we can go ahead and go -2 to 0. So remember, these are the x values. From -2 to 0, it's constant. And then decreasing. Where is it decreasing? And don't read it going this way. You go left to right. So as the x value is getting bigger, what is the y value doing? So as the x value is getting bigger here, the y value is getting smaller. So this is where it is decreasing. It's decreasing from 0 to 2. And so right here is the decreasing part. Let's look at this other example. and it starts out decreasing. So up until that X value right there, what is that X value right there? 1, 2, 3. Oh, wait a minute. It doesn't stop decreasing here. It keeps decreasing, doesn't it? Because, yeah, it's decreasing here, but it's still decreasing. And then it's still decreasing. So really, all of these intervals that if you can connect, that are connected, have decreasing. As the X gets bigger, the Y gets smaller. So this is decreasing from negative infinity to infinity. Now, where is it increasing? Is it increasing anywhere? D. No, it's not increasing anywhere. Is it constant anywhere? No, because it's decreasing everywhere. Okay, so here is some more stuff to read. If f has a local maximum at C, then the value of f at C is greater than or equal to the values of f near C. If f has a local minimum at C, then the values of f at C is less than or equal to the value of f near C. Notice they say near C. The word local is used to suggest that it is only near C, not necessarily over the entire domain, that the value f of C has these properties. So, like for instance, let's see, which example do I want to use? Well, the example that we just used here. That is a local max, but I guess what we're saying is the function could keep going up and this not be the absolute max. This is a local min, and it is actually the absolute min in this function, but the function could keep going and go down further. This would still be a local min. It's just not the absolute max and absolute min. So let's see what it says here. You can use a graph to locate the absolute maximum and the absolute minimum. Look at the graph of the function. So look at the graph of the function f given in figure 23. The domain of f is the closed interval, and so it's a closed interval from A to B. Also, the largest value of f is f of u. So if we look over here at this function, and let me focus good. Still not really focusing good. Well, anyways, this is f of u. And that point is the highest point on the graph. This point down here is, and that point, when I say point, it needs both an x value and a y value. So the point here is v, f of v. So that's the lowest point on the graph, and that's the highest point on the graph. So this is the absolute maximum, and this is the absolute minimum. So what it's saying over here is the largest value of f of u and the smallest value of f is f of v. These are called respectively the absolute maximum and the absolute minimum of f on AB. Okay, so the absolute maximum has to be greater than or equal to any y value on the graph, and the absolute minimum has to be less than or equal to any y value on the graph. Now, when we look at this, this is also a local max and a local min. So sometimes when you have a local max, a local min, you also have at the same point the absolute max and absolute min. So let's look at this definition. Let f be a function defined on some interval I if there is a number u and I for which f of x is less than or equal to f of u for all x and I, then f has an absolute maximum at u, and the number f of u is the absolute maximum of f on I. And then it says the same thing about absolute minimum. And then we've got an example with this. Let's go down and look at this example. Oops. Okay, so in these examples, we want to find the absolute maximum and the absolute minimum if they exist, and also identify any local maximum values or local minimum values. So let's start going from left to right, and the first x value is 1. So f of 1 equals 4. You can see that from here. This is 1, 4. No, that doesn't show up real well. This is an absolute max. And it's of y equal 4. So the absolute max, you would say, is 4, but where it occurs is 1. And it's an absolute max because it's higher. It's the y value is higher than any other y value. Now, right here, we have, and this is f of 5, which is equal to 1. We have an absolute min. That's the lowest point on the graph. Now, what about in between? What about f of 2 and f of 3? Well, if you look at it at f of 2, this y value is lower than the y value to the left and to the right. Because remember, for it to be a local max or min, it only has to be lower than the y values near it. And so if you just look to the left and look to the right, if the y values are higher, then it's going to be a local min. If the y values were lower, it would be a local max. So we see at f of 2, there's a local min of y equal 2 at x equal 2. This is the sunlight again. Let's see if we can get out of the sun. Okay, and then the other place was here at f of 3. Which was equal to 3. And here, the y value is higher than the y value to the left and the y value to the right. So this is a local max of 3 at x equal 3. Okay, let's look at the next example. And let's start with over here at 0. Right here, this point, 0, 3. So the point 0, 3, is it, well, it can't be a local max or a local min because it's at the end point. It's at where the x value ends, basically. So there's nothing to the left to say that this point is higher than the y values to the left and to the right. You can't say that, so it can't be a local max or a local min. Now, is it an absolute max? Well, absolute max and min can occur at the endpoints, but here it's not because there are y values that are higher than that. The y value here is 3. The y value here is 4. So you would say no extrema. Extrema means mins and maxes. And so if you don't have anything here. Now here at 1, 1, well, it's a local min. Because you see when you're down here, you're lower than, or the y value is lower than the y values to the left and to the right. Is it the lowest point on the graph? Yes, so it is also the absolute max. I mean, absolute min. Okay, and then the other point, let's see, at 3, 4, what have we got right here? It's a local max. Because we see that it's the highest point on the graph. Is it also an absolute, or because it's a local max because it's the highest point near x equal 3, so to the left and to the right, but it's also the absolute max. Because you see that's the highest point on the graph. So we would say that at x equal 3, f of 3 equals 4 is a local max and absolute max. And then I guess we've got this last point right here. So let's go over here and do the last point, and that was 4, 3. Well, it's not it can't be local max or min because it's at the end point, and it's not the lowest point, and it's not the highest point. So we would just say no extrema for that one. Okay, let's see what we've got next. And let's look at these two examples. At each marked point, state whether there's a local max, a local min, an absolute max, or an absolute min. So let's just do what we did before. Let's go left to right. So at f of -1, which is 1, it can't be a local max or min. Is it the lowest point on the graph? No. Is it the highest point on the graph? No. So there's no extrema. And then let's go to the next x value, which is 0. So f of 0 is equal to 2. And we're right here. Well, it's not, at the end point, but is it a local max or a local min? Basically to be a local max or local min, one thing you'll notice is that the graph changes direction. So here it's increasing and then it starts decreasing. When we're at this point, it's increasing and it doesn't change. It just keeps increasing. So that is no extrema. There's nothing there either. And it's not the absolute max or min. Now, f of 1 equals 3. Now, is that an open circle right there? If it's an open circle, we really would have to say that f of 1 does not, oh, well, wait a minute. It's got the 0.13. Well, okay, let's just pretend like that is filled in, and then that will make it a little bit clearer. So this would be the absolute max, and it would be a local max. And then let's look at f of 2, 0, or f of 2. Okay, so then the next place to look is f of 2, which is equal to 0 here. Now, I'm going to go ahead. I'm not going to fill this one in. It's an open circle. So there's an open circle there. Let's go ahead and deal with that open circle. So it's not a point on the graph. It's just a placeholder right there. So that means that 2 is not in the domain. Of f. So, I mean, if this point is not even on the graph, then it can't be an extrema. So what that means is no extrema here. And then the last point is where f of 3 equals 1. Well, it can't be a local max or a local min because it's at the endpoints. And it's not the highest point and it's not the lowest point. So you would say no extrema. Okay, let's look at this next example. Okay, so let's just leave on. We kind of put a line right there. Let's see what we can do right here. So at x equal 1 or x equal -1, is there any extrema here? It's at the endpoint, so it can't be a local max or a local min. Is it the highest point on the graph? Is it the lowest point on the graph? No. So we would say no extrema. And at x equals 0, now there's definitely a local min there. But is it the absolute min? No, because see, this graph is going to keep decreasing right here and go down to negative infinity. It's going to keep going. So it's a local min, but it's not an absolute min. Now at x equal 2, which is right here, there's a local max. But is there an absolute max? Is that the highest y value on the graph? Yes, it is. So it's also a absolute max. And then this is an important theorem, the extreme value theorem. If it's a continuous function, which you don't really know what that means in college algebra, but it means it's a function that doesn't have a hole in it or anything. You can draw it's a smooth connected curve and you can draw it without lifting up your pencil. Like this, the example up here with the holes in the graph, that's really not continuous. If it has a hole or a break or anything like that. But if it's continuous, its domain is a closed interval AB. And F has an absolute maximum and an absolute minimum somewhere on AB. So it's just saying, if there's a closed interval from A to B, there's going to be an absolute max and an absolute min on that interval. That would be the absolute min, and that would be the absolute max, whatever those values are. Okay, and then it says the absolute maximum or minimum can be found by selecting the largest or smallest value of f from the following list. The values of f at any local max or min of f in the closed interval, or the values at f at each endpoint of, and so the closed interval AB. So that means look at f of A and look at f of B. This is where the absolute max can occur for men. Okay. So let's go to the next page. The next thing we're going to talk about is using a graphing calculator to approximate local max and local min and to determine where a function is increasing or decreasing. So you can use the graph of the function, and the ones that we were looking at had the x values and the y values labeled. But a lot of times we just say, you know, what is the absolute max or the absolute min of a function in a particular interval? And we don't have it labeled, so we need to figure that out using our calculator. So that's what we have here. I've got my calculator. Go to the next page. And let's see, what function was this? Well, let's just do a polynomial. So let's say that we've got a function, and let's just say it is maybe x cubed. So I just made up a function that's probably going to look similar to the one I have graphed. I'm not sure which one what function that is. But let's look at the graph of this is 2x cubed minus x plus 1. So f of x is equal to 2x cubed minus x plus 1. And here it is when I graph it, and it looks like this. So we can see that there's a local max and a local min around here, or it looks like there is. So actually, though, not sure there is, if it is changing the y value. Let's go look real quick, because this may not work. Let's trace, and let's go, let's see, where am I? I want to make sure that the y value right here, it's 1.19, and then yes, it does go, it decreases for a little bit right in there. So I've got a local max, and they're real close together. But if I go second function calc, it has a minimum and maximum button. It's really dark right now. So we could press, say, maximum. Let's do the maximum first. And what it's going to want us to do is it wants us to position ourselves near that local max and go to the left of it, and then go to the right of it, and then press enter. And it's going to give us the maximum value there. Now that's an approximation. So it says at x equal approximately, what does that say? Minus 0.41, f of minus 0.41 is equal to 1.27. So I had to pull that up to look at it. But that's what this is saying down here. So we've got a maximum value right here. Now, and that's a local max. This is not going to have an absolute max or an absolute min. But if we want to figure out, because it looks like it turns and then it turns again. So it goes up, it has a local max, and then it turns and it has a local min down here. So let's do this. Let's go second function calc, and let's do minimum. And that's option 3, I believe. And so now we want to be closer. Well, we could just hit enter right here, because we're to the left of that, that local minimum. And then if we just go to the right, it found it. Okay, so it found the local minimum, and that value is, and so this is my local max, and this is my local min. And it says that this occurs at about 0.2128, I guess, and F of 0.2128 is approximately 0.8065. Okay, so I just got that from the bottom of the screen here, and that's the min, and that's the local min. So let's see, does that look right? That's the local max, that's the local min. Now, it doesn't matter whether the X value is greater than like in the local min occurred at a negative, the local max occurred at a negative X value, and the local min occurred at a positive X value. That doesn't matter. What matters are these. This is the highest Y value when you're close to right here, or right here, really. When you're close to right here, this is the highest Y value. And when you're close to right here, that's the lowest Y value. So we have a local max and a local min. So I'm looking at another one. I found out what this was, the equation for this graph. Excuse me. It's x cubed minus 3x plus 2. And so I graphed it on my calculator as well. And I'll just show you again how you can find the local max and the local min. And this will not have an absolute max or an absolute min, because these keep going this way and this way. So I'll just go second function, calc, and I'll pick maximum, which is 4. And then I want to be to the right of the max. Okay, so the right, I need to click on this side. And then, oh, wait a minute. I don't think I made a mistake. Let's try it again. Second function calc, and let's go option 4. And then this is it. At first, we need to be to the left. So I'm trying to get over to the left. Am I to the left? Yeah. Let me hit enter. And then I want to be to the right. And then it just says a guess. You could go up closer here. And then it gives me this answer. So the local max, X is approximately, well, it's approximately 1, and the Y equals 4. Okay, then the local min, let's try to find it. So we'll go second function calc again, and we'll go to the minimum, and then it wants us to be to the left of it. So I went too far really to the left. Let me just go back over here. Okay, that's to the left, and then it wants me to be to the right, and then a guess. Okay, and it says now the local min is actually, gosh, that's approximately 1 as well. And it says X equal approximately 0. Let's look at this for a second. This looks like it's at 1. I think this was supposed to be at -1, and that's, yeah, -1 over there. And so, yeah, -1, that looks right. So that's what the difference is. It looks like if you put a 1 in here, you would get 1 minus 3 plus 2, which would be 0. So that's the local minimum. Now the local maximum, if you put a -1 in here, you would have a -1 cubed minus 3 times -1 plus 2. So that would give me a -1 plus 3 plus 2. Oh, yeah. And so that would give me 2 plus 2, which is 4. Okay, so that looks good. Let me get the sunlight out of the way here. So we've got a local min or a local max at x equal -1 and a local min at x equal 1. So that's what happened here. And there's the calculator. This is where I put it in. So to put it in, just to make sure you know how, you go x and then you use this for your exponent. But if you have one of the newer calculators, you need to use the arrow to get out of the exponent. And then you go minus 3x plus 2. And then you can hit graph. I got that in there right. No, for some reason, I've got a plus sign there, and it should be a minus sign there. And then let's graph. Yeah, there we go. So you go over to the y equal to enter. Okay, let's see what we've got next. This is the one I just did. Not sure what that is. So the next thing we're going to talk about is the average rate of change. And this is a formula that you need to know. It's very similar to the, or it's somewhat similar to the difference quotient. Get this where it's going to. Okay, so here we go. This looks a little bit better. In foundation section 3, which you're not in foundations, we said that the slope of a line can be interpreted as the average rate of change. To find the average rate of change of a function between any 2 points on its graph, calculate the slope of the line containing the 2 points. So really the average rate of change is just the slope. Now, why we don't call it the slope? Well, if you think about a curve doesn't really have a slope. It depends on between what 2 points you're talking about. Like the slope there is probably going to be negative, but then over here, between these 2 points, it's going to be positive. So we don't say slope. We say the average rate of change between 2 points. Now, if the graph was linear, then the average rate of change would be the same as the slope. I'm sorry, guys, I'm losing my voice. Okay, so the way the average rate of change is defined is if A, you've got A and B, and A is not equal to B, and they're both in the domain of the function y to the f of x, then the average rate of change of f from A to B is defined as, and this delta y over delta x, that just means the change in. Delta means so the change of y over the change of x, or in other words, this is what we use, f of b minus f of a over b minus a. So let's know this. Let's know that formula. So we can calculate the average rate of change. And over here in words, it says, the symbol, oh, it's just talking about this symbol and its red changes. I already told you that. So let's just do some examples. So we want to find the average rate of change from 0 to 2 from that function. So from 0 to 2, remember the formula the average rate of change equals f of b minus f of a over b minus a. Now, they've given you 2 points. So these in this point where they said from x, from 0 to 3, so that means from x equals 0 to x equal 3. So you know what your x values are, so you just substitute them in. So you're going to go f of 3 minus f of 0 over 3 minus 0. And then this function is, let's write down what it is. F of x is equal to, it's a minus x cubed plus 1. Okay, so what we're going to get over here is, if we need to find f of 3, we've got minus 3 cubed plus 1. Oh, I couldn't even read that right. That says 3, and that says 2. This is a 2 right there. So let me fix that. That should be a 2. Oh, this should be 2. I just couldn't see. This is a 2, f of 2 minus f of 0 over 2 minus 0. And so this is going to be minus, and then we're going to go 2 cubed plus 1. And that will be over 2. 2 minus 0, which is 2. And then that's just the f of 2. I've also got to subtract f of 0. F of 0 is just going to be a 0 cubed plus 1. So what we have there is a minus 8. This will be plus 1 over 2, which is, oh, I'm sorry. And then I've got a plus 1 there and a minus 1. And so that's just going to give me minus 8 over 2, which is equal to minus 4. Okay, now we want to find the average rate of change from 1 to 3. So that was the A part. Let me see if I can get the B part in somewhere. So the B part, we know the formula and we know the function. So we're just going to go straight to do that. So we're going to find f of 3 minus f of 1 over 3 minus 1. Okay, so f of 3 is going to be, it's going to be minus 3 cubed plus 1. And then f of 1 is going to be minus 1 cubed plus 1. And then this is going to be over 3 minus 1, which is 2. Okay, so let's see if we can figure out what this is going to give us. This is going to give us a minus 27 plus 1, and then plus another 1, and then minus 1 over 2. So what that's going to end up equaling is going to be, I believe, a negative 13. Let's see if that's right. Okay, let's see, that would cancel. That would be, let's just put this down. That would be a negative 26 over 2. And so, yes, that would be negative 13. So that's the average rate of change. So the negative 13 is the average rate of change of the function between these 2 points. So, you know, if you look at the function, let's just look at the graph of the function real quick. Y equal, and it's a negative. Let me turn it on and let's clear that out. So it's a negative x, and then I want to cube it, and then I want to get out of the exponent and then it's plus 1. Okay, so the average rate of change between 0 and 2, so between 0 and 2, is different from the average rate of change between 1 and 3. So, and let's see, we got different values here. We got a -4 here and a -13 here. So actually, if you look, it looks like it does start decreasing faster right there. And so that's from 1 to 3. So that's going this way. Okay. Here's another example down here. We'll do this too. So find the average rate of change of h of x equals x squared minus 2x plus 3 from -1 to 1. So the average rate of change in the first part, and this is A, is going to be equal to f of 1 minus f of -1 over 1 minus a -1. So be careful there. And then we figure out what f of 1 is. Well, it's 1 squared minus 2 times 1 plus 3. And then we're going to have to subtract minus 1, f of -1. So that's -1 squared. This. And so it's -1 squared minus 2 times -1 plus 3. And so that's all over 1 plus 1. Okay, so let's see what we get here. We get a 1 minus 2 plus 3 minus a 1 plus 2 plus 3 over 2. So I think we get 1 minus 2 is -1 plus 3 would be a 2. And then 1 plus 2 plus 3 is going to be 6. So this is going to give me a -4 over 2, which is a -2. Okay, and so I think that's how that one worked. Let's look at that just for a second. Did I make any mistakes? Probably so. I think that's right. Okay. So I think that's all we got. We have one more example. Okay, one more example to tie some of the things that we've learned together. Then this will be the last. And it says the graph of a function is given. Use the graph to find the intercepts of any, the domain and range, the intervals on which the function is increasing, decreasing, or constant, and whether the function is even, odd, or neither. So here's our function down here. And so let's look at the first question, which is about the intercepts. Does it have any x-intercepts? Well, that would be where it crossed the x-axis. And that looks like it's at x equal 1/3. And it looks like there's another one right here. And I don't know exactly what that is. But let's say it's 2.5. So those are the x-intercepts. The y-intercept, where does it cross the y-axis? Right here. And so that's at y equal 1/2. Or you could write out the ordered pairs either way, doesn't matter. Okay, then that was the A part. Now the B part says the domain and range. Okay, well, it doesn't have arrows that keep going. So for the domain, remember that's the x values. It starts over here at x equal -3, and it includes -3. And then it goes over here to where x equal -3. So it goes from -3 to 3, from -3 to 3. That's the domain. Now, the range, how far down does it go? Start with how far down does it go? Well, the lowest it seems to go is -1, because you know now we're talking about y's. Here we were talking about x's. So, and then what's the highest it goes? Up to here, up to 2. So that's the range. Now, the next question says the intervals on which the function is increasing, decreasing, or constant. So let's look at this. It's increasing right here. So that's from x equal 2 to 3. And it doesn't matter. You can put brackets or you can put parentheses, because we're really talking about what it's doing on an interval, not so much at the end point. So you can either include them or not include them. Just, I don't know which one the My Math Lab homework wants. It might want it like this. Now let's look at where it's decreasing. Okay, so we got to go back up there and look at the function. Where is it decreasing? It's decreasing right here. And let's see, that x value, I believe, is -1. And so it decreases from -1 to 1. And then where is it constant? It does have a couple places where it's constant. It's constant right here. So that's from -3 to -1. And you really shouldn't say union here, although sometimes people do. Where else is it constant? Right here. And remember, we're putting in the x values and on 1 to 2. Okay, and then it had the last question. Is the function even, odd, or neither? So if we look at that function, does it have symmetry about the y-axis? No. Does it have symmetry about the origin? If it was going to have symmetry about the origin, for one thing, I can look at it and tell that it doesn't, because if I flip this down and over, it wouldn't end up on the other part of the graph. Also, you see, like right here, you have f of -3, you have f of -3. So I'm going to say neither even nor odd. And look right here, there's the point -3, 2 and 3, 1. So f of -x doesn't equal f of x, and f of -x doesn't equal the opposite of f of x. So it's not even or odd. If this were true, that would mean it's even. If this were true, that would mean it's odd. So it's neither even nor odd. And I do believe that is the end. Okay, I believe that's it. So guys, I'll record another one as soon as I can. Y'all work hard. I'll see you.